Hello, everyone. Thanks for having me. I will tell you basically almost everything you may want to know about transformers. So this is going to be deep dive into the architecture, into quite a few of the details, and then I will show you how they are adapted in all different kinds of communities recently. So yeah, there will be a few sections in the talk where I will make very clear break for questions and take as many as the time permits. But as Susanna said, you can write them in between in the chat. So how did it used to be? Like, how did the landscape in research and in ML used to look like? Kind of like this. We had the different fields like computer vision, NLP, speech, translation, RL, and many more that I don't all list here. And basically each field was like its own little bubble, barely looking at the other fields. Long time ago, it was still possible to follow the other fields, but then as everything exploded, like people cannot read the papers from everywhere anymore, and everybody is kind of isolated in their bubble. And each of these fields, over time, developed neural net architectures that sound like they perfectly fit this field or the data that this field typically use. So a couple examples here. I'm not going to go through all the details. But for example, in computer vision, we usually look at pictures, sometimes videos, and they kind of make sense that if I want to, let's say, detect or describe things in pictures, that I should recognize them the same way no matter where they are. Like this, I would say this is a robot hand, no matter whether it's here or whether it's in this upper left corner, right? So with this intuition, people then develop the architectures based on this, which are based on mainly convolutions, which fulfill this property, and some pooling things. And this is the classical convolutional neural nets that I'm sure like 99% of you know. Similar story in language and natural language processing, right? All languages go in, or vast majority of languages go into in one direction, like from left to right, or from right to left, or maybe sometimes from top to bottom, but basically from start to end of the text, right? And so this inspired this class of neural net architectures, recurrent neural networks, LSTMs being the most famous one, that process the input one thing at a time. Like here, we take the first character, for example, or it could be word or something. We process it, track some state about our current knowledge, then go on to the next. Read in the next input, like character or word, process it and merge it into our state, and continue, and so on and so on. There can be various complicated ways of merging it into the state, which then become the different architectures like RNN, LSTM, GRU, and so on and so forth. But it's essentially it, right? Go one by one in the order that is natural for the language. And then at the end, have your output, for example. Jumping straight to translation, it's a similar story, but you don't have the output at the end. But at the end, your output, you start generating the output, again, one thing at a time after another, usually again with the LSTM or similar RNN. In speech, deep learning seems to have had a slightly harder time, but the first maybe purely deep learning encodes type of architecture that became somewhat dominant or widespread in speech was based on restricted Boltzmann machines, which you trained layer by layer, and then fine-tuned completely eventually, which is again very different from the things we see here. Yeah, and then there is RL, where the architectures are usually kind of, I don't want to say ridiculous, but tiny and not engineered at all. And it's all about like the learning process around it. Maybe recent, or not that recently, there was a Gale and behavior cloning that kind of picked up a bit of steam, which is offline RL. And so this offline RL is more similar to the classical supervised learning, where you have your data set and try to learn something. And for example, gun-like thing became popular there for Gale. All right, so the bottom line is very fragmented, everybody with their specialized architectures that make sense for their tasks, and that's about it. Then appeared the transformer. It took a little bit of time, But now it kind of looks rather like this. This is the picture of the transformer architecture from the original paper. And basically now all the communities are heavily looking into using the transformer architecture, and sometimes almost exactly the same one, as we will see towards the end of the talk. I think, yeah, you can hate it or like it. I think it's pretty cool because it allows the communities to start looking more at each other again. And, you know, maybe in computer vision, we notice some instabilities in some settings, and then we can look at natural language folks. Oh, they also had the same ones, and there is these 3 papers that tackle them. Maybe this will work for us, right? I believe this allows more knowledge transfer between the communities to be less fragmented. So I like that. This is a bit exaggerated, right? CNNs are still used by people, RNNs are still used by people sometimes. But you can say that Transformer picked up steam a lot and a large share of the mindset in each community. That's a thing that happened in the last couple of years or so, or last few years. And so now I'm gonna first give you a little bit of background, and then dive deep into the transformer architecture, what it looks like, what all of the pieces mean, and starting with the attention mechanism that I will describe in detail. So there's probably quite a bunch of you who already know this, maybe even already implemented your own transformer from scratch. For you folks, this part may be boring, but for everybody else, I hope this will be interesting. And after that, you will feel confident that you understand what is the transformer, what is attention, how does it work, and that you may even be able to implement it yourself. And then after that part, I will cover into like each of these communities, how exactly did they adapt the transformer, what does it look like, what are commonalities. All right, so let's get started with that. So first of all, the transformer appeared slowly over time in the translation community. And the first sign of it, at least that I'm aware of, is this 2014 paper by Dmitry Badanov, Kyung-Young Cho, and Joshua Benjo, which was called Neural Machine Translation by Jointly Learning to Align and Translate. And they had this picture that if you already know well self-attention and you squint a lot, you might recognize this maybe attention mechanism, but it's a really not very self-explanatory picture. And the key thing of this paper was that, wow, when translating, we can now automatically learn to align which words in one language become words in the other language. Here is an example between French to English. Let me see if I find it. It has a nice example place. Like here, yeah. When you want to generate the French, in French, you have this le, la, like it's either female or male, the word. And so depending on what the word is, female or male, the word that comes before would be either le or la, would be different. And it doesn't make sense which word is male or female, it just is. And in English, you don't have that. Any word always is preceded by the. There is not 2 versions of the, right? So when you want to generate the French, this thing that comes before the word, you actually need to look not only at the, but also at man in order to know what word comes next, such that you know what to generate here, right? And this heat map shows, wow, the model figured this out, that when generating this, it looks at both of them. And this is through this attention mechanism that they introduce in this paper that learns to do this alignment as part of learning to translate. Interestingly, so this paper basically designed or invented the attention mechanism used in transformers, but the word attention appears only 3 times in this paper, and not even in like interesting ways, just saying like, okay, pay attention, we have an attention mechanism, and then never says it again. It was 2014, and then it took a whole 3 years to 2017 for the transformer paper to come out, and like to make this very established thing that everybody pays attention to. This paper, the transformer paper, was called Attention is All You Need, because they built a whole neural network architecture on top of this attention mechanism and kind of throw away all of the things that I mentioned before, like convolutions or sequential processing with the state, like in RNNs and so on. And look, how far can we go by using only attention? And so now I'm going to spend a bit of time explaining the attention as introduced there and used everywhere now. in very much detail. So the first thing I should say that when you think of attention, maybe try not to think of like attention in the classical sense of the word, but it's kind of a dictionary lookup in Python. All right, but it's not discrete. It's kind of a soft dictionary lookup. And let me tell you exactly what that means and how that works. So typically you have or the function that attention represents or can model is this. You have a query, you have keys and values. So just like in a dictionary, right? You have the keys and you have a value. For each key has a corresponding value. And then you want to extract the value corresponding to a key. And this is with your query, right? So you want to query the dictionary to see what value is there stored in my query. So what do you do then? So, and I should say here in attention, each of these things are vectors. So this is what is represented here. So vectors of floats. Your query is a vector of float, keys are each a vector of float, and values are each a vector of float. Then the first thing you do is you compute the similarity between your query and each individual key. This is usually done just by the dot product. So if the vectors point to the same direction, the dot product is 1. If they point to opposite direction, it's -1, right? And then everything in between, depending on how similar the vectors are. Oh, that would be if they are normalized, but if they are longer, then it's anyways a large positive number if they show in the same direction, large negative number if they show in opposite direction. Yeah, and so basically for each product between the query and the key, you get one number as a result, right? So for all of these products, you get one number per key as a result, which means how similar is this key to our query. And these are called the attention weights. And they are usually such that we can like do something meaningful with them. They are normalized, and we use the softmax function to normalize them, such that now they kind of represent a probability or a weighting, if you will. So now imagine we have many keys, and I come with one query. Let's imagine out of all of those keys, one is very similar to the query and all others are not. So the one that is similar would have a high value in the attention weights and all others would have a strongly negative value because they are dissimilar. And then we take the softmax, so the attention weights would become very close to one hot encoding with zeros on all the keys except for a 1 on the key that is super similar. Then the next step is we take a weighted average of all the values where the weights are exactly these attention scores. And so attention score time value plus attention score time value plus attention score time value and so on gives us a vector as the output, a single vector again, right? And if we have the case that one key only is very similar to the query, then this is mostly zeros except for a single one, then the result of this weighted sum is mostly just the vector that corresponds to this very similar key, right? And so the output would be very close to the one of these value vectors. So far, so good. So far, this is really a very convoluted way of just saying dictionary lookup, right? Give me the value for that query. But I said soft dictionary lookup. So let's take another example. What if in the keys there are now 3 of them that are really similar to the query and all others not? Then here, at first, we have 3 numbers that are highly positive and all others are highly negative. Then taking the softmax, we actually have all zeros except for 3 locations. Each of them is a third, right? 0.333, 0.333, 0.333. And then when we take the weighted sum of these values, we are actually averaging the 3 value vectors, which corresponds to these 3 very relevant keys. And so the output is the average of these 3 values. And this is where the soft part comes in. And this is what even allows to learn all of this thing with backpropagation. Okay, so this is attention mechanism in a nutshell, or like the core part of attention mechanism. Now I started in kind of abstract way, and like this is I look at this in isolation. You will later see how it becomes part of a whole architecture and so on. But I should already mention that usually, like you have a, oh, I should add another one here. So usually you have a set of input vectors that come from somewhere, and then they get linearly transformed to keys and linearly transformed to values. And these transforms are 2 different ones that are learned. And then you have your query, and so you get your output. So you transform the input that is like a dictionary, or that gets turned into this dictionary, and you get one output per query. And you have as many keys and values as you have inputs usually. And the query also often comes from another input that I forgot to draw here, like the Y, and is also linearly transformed to become the query. So this is the attention mechanism. And we often talk also about self-attention. That is when the query is derived from the same input again. You will later see how or why this can make sense. All right, so far so good. Here's the first point where I want to take questions, if there are.
Yes, there are. I think there's always like a little bit of a need for clarifications on the keys and values. So we have, for instance, one question: if you could give like a concrete example, for instance, for language, how, for instance, what does QKV encode from an NLP perspective?
Yeah, this will become very clear later when I show how it's using the whole architecture, but maybe as a sneak peek, you could think as in the translation example before that I showed, right? The query would be the word that you want to translate in the next language, for example, and the keys and values are all the words in your source sentence. And then, right, you want to generate as next like this L apostrophe in French or le la, and then you look at the queries and keys, which are all your words in the English thing, to try to understand what's going on. But this will become much more clear in a few slides.
Perfect, thanks.
Okay, and I see there was the poll. Actually, quite a lot of you implemented transformers already. Surprisingly many, 30%. That's nice. 55% no, and 14% I tried. Maybe after this talk you will try again and it will work, hopefully. All right, so when I said this is the attention mechanism, I kind of lied a little bit. There is a few more things to it that I will mention now, and then we will have the full attention mechanism as used everywhere. The first extra thing is that for almost all practical purposes, we never have just a single query, but we actually have many queries, right? So I show them here, then they are stacked together into a matrix of queries. And then it means we don't have just a single attention vector or weight vector, but again, we can stack them. For each query, we have one, and then we have an attention matrix. And you very often hear or read in papers or see in code the attention matrix. It is the attention vector for each of the queries, which may be many, right? And then the output also is not just one output, but one for each query. So it's also an output matrix. This is relatively simple. The other thing that is actually done in practice almost all the time and everywhere, and maybe a little bit less simple, is that we always use multi-head attention. We always talk about attention because it's simple-ish to explain and think about, but in reality, all implementations everywhere use multi-head attention. And they are often, you will see them described like this. I don't like this picture, and we'll show you a better one next. But basically what it means is we split the input into many pieces and run many smaller attentions on it, and then concat all of this again afterwards. I prefer this view. They mean exactly the same, but it's another way to think about it. So we have our queries. We split them along their like vector dimension into shorter queries, right? So we still have 4 queries, but each of them are just a subpart of this query vector. And then we compute the attention matrix for each of these pieces. So in this case, we cut it into 3 pieces. This would be 3 head attention. So we have now 3 attention matrices of the full size, because they are size number of queries times number of keys, right? And then we have 3 output pieces. Each of them, again, are smaller because we cut everything into pieces, and then we concat them together to a longer output again. This is both more efficient and allows for same compute more flexibility in the model, and just empirically usually works better. And there's some nice theoretical properties, not going into it. But so in reality, you always see this multi-head attention, and it's once you understood it, it's quite straightforward. Cut it into pieces, do many smaller attentions, and concat the results. And when thinking about what's happening, 90% of the time it doesn't matter. So people think about the simple attention, but then in reality use multi-head. And so taking all of this together, this is the formulation. It can be written down very succinctly, like queries times keys to get this attention matrix. This is scaled by some factor for like practical purposes, makes everything work better. It doesn't really matter. And then sent through the softmax. And then this softmax gives us the attention matrix, right, which we multiply with all the values. And so we get back the outputs. So this is the whole attention mechanism in a nutshell. Although, as I just mentioned, here I don't represent the multi-head part of it. There would be extra indices with it. Okay, and this is the attention now that everybody's actually using, implementing, and so on. Yeah, here I will skip in interest of time questions about this, also because it's more implementation details that are not really necessary to understand the gist of attention. But when you look at implementations, you always see this, which is why things may look more complicated than you have in mind. All right, so this is all about attention. And now I want to spend the next maybe 20 minutes or 15 on the transformer architecture, which is network architecture, which is currently taking over the world of machine learning at least, and is based purely on self-attention, almost. You will see there is actually a lot of more pieces. This is the picture of it that comes from the original paper and you see very often. And we're going to walk through it step by step. As I mentioned, this comes from the translation community. So when trying to understand the architecture, really think of the translation task. Like we have some text maybe in English, and we want to generate the translation of it, again, text, maybe in Japanese. And the cool part is that we're kind of lucky that this appeared in translation, because translating something into something is a very general API. You can cast many tasks into this. Like, for example, creating a summary of a video or creating a review of a movie. This is like translating this video into text, for example, right? And you can think many tasks you can formulate this way. All right. So the first part, this is the very first part is not even specific to transformers, but to treating text, is tokenization. Again, maybe a lot of you know it, but maybe not all. So I'm going to explain this. So when you have text, you have these characters or UTF-8 letters, right? But everything I said before about attention and everything you know about neural networks always works with float vectors in some continuous space. So we need to turn the text into float vectors that the model can like use, do computation with, learn stuff with. And this is called tokenization and embedding. First of all, so we have this example text that we want to translate. The detective investigated. First thing is tokenization, which means cutting the text into pieces. There are many different ways of tokenizing, all with their pros and cons. You could think of cutting it into words, but some languages don't have clearly separated words, right? So there's cons. The fanciest, latest tokenization ways that work best kind of split it into word pieces that maybe also cover more than a word, less than a word. So here I just take this example. This is cut into the, detective, invest, egate, and add. So this sentence is cut into 5 tokens in my arbitrary example. Then the next thing that is done is you need to define a vocabulary of all tokens that exist in your setting. This can be quite large. Typical sizes are 32,000 or sometimes 250,000, for example. And it's just a list of all of these tokens, right? And so each token can be turned into an index in this list, right? And often it's ordered with the most frequent coming first, but it doesn't really matter. So for example, the can be turned into the number 3. Detective can be turned into the number 721, and so on and so forth. Right? So now we have already turned the text into vocabulary and the list of integers. Next thing is we can learn an embedding of the vocabulary, it's called. So just arbitrary, randomly initialized vector of floats for each entry in the vocabulary. And then later these floats will be learned as part of the model. So for example, the entry 3 in the vocabulary is this float vector, 0.123, and so on and so forth, right? Each entry has a float vector. And so we can now replace each of these tokens by the float vector that corresponds to it, right? And now we have transformed this sentence into a sequence of float vectors. And like how large are these float vectors is later becomes the model dimension. It's an arbitrary parameter we can choose. Often it's something like, I don't know, 128, 768, or things like that. Like nice computer science numbers. Let's say 128 for this example. So that's one part. Now we have our sequence of float vectors. However, there is one thing. So I said transformer is only the self-attention mechanism. And if you think about the self-attention, like again, just think of it as a soft dictionary lookup. There is no ordering in dictionary lookups, right? And if you dig into the details of the self-attention operation, you will realize that order doesn't matter, right? You can shuffle around the keys values consistently, and it still does the same thing afterwards. But in text and in natural language, order definitely matters. I don't have a good example off the top of my head, but you can imagine a sentence where you switch the order of two words and it means something completely different, right? So we do need to tell the model about ordering of things, like at which position is each word located in the sentence. And this is done with what's called position encoding. And this is specific to transformers, because if you have RNNs, you just give one after the other to the model and the order is natural, right? So for transformers, whenever order of the input matters, we need position encoding. And I'm gonna explain the intuition behind it. In reality, it's a bit more complicated. So for each of the words, we replaced it by this float vector in arbitrary floating point space, right? High dimensional space. And now imagine, just for the sake of the understanding, they are all very close to zero, right? Let's say we initialize them with randomly small values, so they form our whole vocabulary forms a point cloud centered around zero that is maybe not much larger than 1 in radius, right? Then what we can do is that we say the first word, we always add 10 to it across all dimensions. The second word, we always add 20. The third word, we always add 30. So the result is that the first, it's basically for the first word, we take this point cloud, we shift it to location 10 in arbitrary vector space, right? And then we pick the word that is used here. For the second word, again, we shift it and it's elsewhere in space. Third word, we shift it, it's elsewhere in space, right? So via that simple thing of adding a different number for each entry in our sequence, we can tell the model basically what is the ordering of things. In reality, it's not just adding 10, but adding something much more structured and more high dimensional and so on. But it's the intuition behind it. And there are different position encodings. There are whole papers about it. It's a whole research direction, what is best in which cases and so on. But that's the gist of the simple position embedding from the original transformer. Okay. Maybe I take a quick question break here, potentially.
Yeah, maybe one quick question would be, now looking at these encodings, can transformers work with, you also mentioned previously, for instance, to translate a video or to summarize a video. Can they work with very long texts? That's the question.
Yes and no. In principle, they can. And actually, RNNs have an issue, this vanishing gradient problem. Like there's a very clear issue in the RNN formulation as the sequence gets longer. There is not really a fundamental issue with transformers regarding sequence length, which is nice, but there is a practical issue. This attention mechanism, as sequence get longer, is quadratic. It's comparing everything to everything. So if we have a sequence length of like 10,000, it is insanely slow and requires a huge amount of memory. And so it's actually key when you apply the transformer somewhere else to figure out how to transform your input such that the sequence is not crazy long, but it's still long enough. And we will see a few ways later, actually. All right, so I will move on. So now we have our input prepared, and we have a set of float vectors, which also encode their ordering. All right. And now we first send it through a multi-head attention mechanism, or more specifically, multi-head self-attention. And now you can see where the key query values come from. Each of these float vectors from the token is linearly projected. So it's transformed into a query, into a key, and into a value. And then you do self-attention. So attention from all of these queries into all of these keys and values. So basically each vector, think of it that each vector looks around what other vectors are there in my input, right? And then computes the output based on this, on what other things it has seen. Okay. Think of it for now as the output being somehow this token manages to update its representation. Like it looks around, sees what's going on, and updates its representation. We will see later how exactly it updates its representation. Okay. So that's how the self-attention is used here for the tokens to look around what's going on. Then there is this feed-forward block, also called pointwise MLP, also sometimes called one-by-one convolution. This is then after the attention, after every token has looked around, then every token individually is sent through a MLP. So I like this formula actually. So the input is multiplied by a matrix, bias added, nonlinearity, multiplied by a matrix, bias added, and that's the output. So that's a very traditional multi-layer perceptron. GILU is usually the nonlinearity used. And the thing depicted here is this is usually huge. So the intermediate representation here may be large, like 4,000 dimensional or something like that. And this transform is done independently for each token. They don't, in this transform, they don't look at the others at all. You can think of this as basically the token, after it has seen what's going on around it in this multi-head attention previously, now it's given some time and processing power to think about what it has seen. Okay. There is a different papers trying to investigate what is really learned in this MLP. And there is starting to be some evidence that this MLP encodes world knowledge. Like, for example, that Obama was the US president in what, 2008, for example. I hope I got this right. Right. So, for example, this, or that, I don't know, Conan is a popular detective in animes, right? So, for example, then here, after it has looked around and has seen detective, somewhere where in the weights is stored that, yeah, it can be likely that we're talking about Conan or other popular detectives, right? Okay, so think about this as processing, give a lot of processing power to think about what it has seen and storing world knowledge that it has learned during the training. It gets encoded in these weights, very likely, not 100% sure. This is also where most of the parameters of the architecture lie. So why that means that there can be a lot of information stored there during training. And these efforts of going towards gigantic transformers and mixture of expert transformers and so on, large majority of them focuses on this block, because it has also been shown that scaling this block to larger and larger gives you the best bang for buck. All right. And yeah, because it is the same operation applied on each individual input, some people like to see it as a one-by-one convolution. If you don't get it, never mind, it's not important. Now, one thing that is often swept under the rug, but I think is really important to understand is residual connections. They originally come from the ResNet paper in computer vision. And they are a very simple thing. They mean basically if you have some module or operation that you apply to your input, then the output of this module, just add your input to it again. And told like this, it sounds like complete nonsense. But in this residual nets paper, it was, for one, it was shown to improve trainability a lot. And it had good reasons for it. Like the gradient path from output to every single module becomes a lot shorter. But I also like one particular interpretation of it. So this is the one that is usually, both of these pictures are the exact same thing, Usually this one is shown in papers, presentations, lectures, and so on. And it says, okay, skip connection is this residual connection. And this is exactly how we read this, right? You have this processing block, and to its output, add back the input. I don't like this view. I like this view, which is the same, just moving things a bit to the right. But to me, this looks like, okay, we have our X, and then we have some processing that goes on and updates this X a little bit, right? And this is how I think about residual connections. And this is how, now what I mentioned earlier, you can imagine this multi-head attention. After looking around, it's because there is a residual connection, it actually uses a self-attention mechanism to look around and propose an update to its own representation via this residual connection. The next thing is that there is layer norm used a bit everywhere. This is not is technically important, but I think to understanding things for the large majority of cases is not that important. It's a normalization on the activations that makes training nicer, things easier to optimize, and so on. Maybe one thing to know is that there is nowadays two big classes of transformers, post-norm and pre-norm. They only differ in where they put the layer norm. Do they put it here, and then it's used both on the block and before the sum, or do they put it only here, only into the block? And I think it's not clear which one is better. Like you see sometimes arguments either way in different papers. But it also doesn't really matter that much, I think. So taking all of this together, we have just seen the encoder. You repeat this typically 6 or 12 times. So self-attention to look around and update your knowledge what you've seen around. And then the big MLP block to really process what you have seen. And then repeat this, repeat. So then you can think of the output of the encoder. This is as many vectors as we had as input, right? But each vector now you can think of it as a heavily processed version, or like very high level, contextualized. It has seen stuff, it has processed stuff a lot. So it's very high level information version, transformed version of our input. So in terms of translation, our input was English text. This is very high level, let's say understood representation of this English text. But this has not yet anything to do with the output we want. We didn't generate any translation, right? This comes in the decoder, the right-hand side part here, that will generate the output. Now, how do you even generate translation? So the aim here for the decoder or this type of model is to learn to represent the probability distribution over all possible outputs, and then essentially sample from those. All possible outputs would mean, for example, all possible sentences in the target language, in Japanese. We want the distribution over them. And for translation specifically, we want the probability over all possible Japanese sentences given our English input sentence, right? Given the detective investigated, what's the probability of, and then Japanese sentence 1, Japanese sentence 2, and so on, millions and millions of them, right? And then we can sample the most likely one. For example, just take the most likely one, gives us one translation, sample from the 10 most likely ones, gives us 10 likely translations, and so on. But this sounds completely crazy and impossible. But there is a nice property that we can use to make it look immediately much more tractable. And that's the following rule of probabilities. We can decompose it, right? Z is a sequence of tokens of arbitrary length, but let's say a fixed length for now. So we can decompose this as probability of the first token, given the English sentence, times probability of the second token, given a specific first token in the English sentence, times probability of the third, and so on, and so on, and so on. And this way you can actually generate or sample one token at a time. And there is an exact equality here. So this is exact, there is no approximation. Yeah. What does this mean regarding our model? So each P is a full pass through the model, where input, do I have it here? Yeah. Where the input is here, or full pass through the decoder is this P, where given is X, this is what comes from the encoder, our translated English sentence, and what have we generated so far? Like for example, Z1 and Z2, the two first tokens in Japanese that we have generated. These are the inputs to the decoder, and then the decoder outputs probability distribution over the third token. Like how likely are, and then all of our vocabulary tokens. All right, so if we can model this, we just, after one forward pass through the model, we have our probability distribution, and we need to choose one of the tokens. We can take the most likely one, that would be greedy decoding. We can keep track of a few and try all of them later, and so on. These are decoding strategies. There are many. I'm not going to go into detail. Just think of taking the most likely one, and then do another forward pass with our context, X, and the token we just picked, and then we get the distribution over the next token, and so on. Okay, this is high level how the decoder works. Now a bit more low level, how the decoder works, or how the decoder in transformer looks like. Again, we have this as input, the things we have generated so far. Again, these are tokens. Then we have this embedding and positional encoding. And then we have self-attention, again, to process them. But there is a little trick. Yeah, I'm getting a bit short of time. So I'm going to give the high level of the trick, because this, what I just described, this generation is extremely slow, right? And if during training, for each training example, you need to do all of these forward passes, depending on how long the training example is, this is crazy and you'll never be able to train this. So there's a couple implementation tricks to make learning decoders faster. One at training time, one at testing time. At training time, the trick is that we can actually pass the whole sentence, like all inputs, all target texts. This is training data, so we know the translation for this example, right? So we pass all of it through the transformer. But in this self-attention, the self-attention matrix, we multiply it by a mask matrix, which is a triangle of zeros and a triangle of ones. So for the first, or let's say for the first token, we mask out its lookup into all of the future tokens. So we can basically not look at the future, because the future in principle has not been generated yet, right? That's how we want to use the model. And so this is called the causal mask. And once you have, if you use this during the training, then this is a very nice property of the transformer. That's all you need to do to become much more efficient at training and to be able to process the whole sentence and in one go at training time. So this is many P evaluations in one at training time. And at generation time, there is not this kind of trick. We really need to generate each token one after another, because in order to compute P of Z3, we need to have concrete P of Z1 and 2. So we need to have sampled them first. But there is some caching mechanism you can implement, and are usually implemented in the efficient implementations that make the code a whole lot easier, but are really just like things we have computed before. We keep them in mind for the next, or we remember them for the next time, classical caching. Not going into detail there. Here is where the translated sentence comes in. This is the cross attention. So the original sentence we want to translate comes in, and this is cross attention or regular attention. This the tokens from the decoder now become the queries, and the encoder becomes key and values. So this is where the token that I am trying to generate right now, or to figure out what should I generate right now, can look at all of the tokens from the source sentence. And this is where we can then learn this alignment, for example, from the original attention paper, right? So each decoder token can look at all of the encoder tokens and figure out what it should translate to, basically. I'm gonna skip, for interest of time, more explanation of this. And yeah, and then there is just the MLP block again, this feed-forward layer. And we repeat this. So the decoder is first self-attention, causally masked self-attention, if you want. Then cross-attention, attending into the encoder's output. Then MLP layer to process everything we have seen so far. And again, repeat this 6 times, 12 times, depending how deep is your model. And then at the output, right, again, we have output for each token that we already generated, plus the one we currently want to generate. And this is then transformed with just a linear and softmax into probability distribution over all possible tokens. And then sample from this, take it and pass it here into the input again. I'm gonna go quick over this. Yeah, so this is a summary GIF from the original transformer blog post, which I think is quite nice. So this is the encoder. Everything attends to everything and creates higher level and higher level representation. Now the decoder starts with nothing. This is the cross attention to the encoder states, and then samples the first word. Then self attention first to what's generated so far, cross attention to all the encoder states, and generate the next word, and so on and so on. So this is test time generation that is shown here. Right. Okay, I like this animation. Then there is one important thing to note. People always think of transformer as like crazy large model, insanely slow, needs tons of data. Only one of these is true, needs tons of data. It works very well. It's a very flexible architecture, so it works very well when there's lots of data. But it's at the same time the disadvantage. It's extremely flexible, so if there is little data, it is very prone to overfitting, more than CNNs, RNNs, and so on. But it's actually very efficient. One key result of the original paper was that in translation, it was like 2 to 3 orders of magnitude more efficient than the previous existing translation models, and getting better results. Right? I just want to highlight that and to remove the impression that transformer is always super slow, needs tons of compute. All right, so this was about the transformer architecture. I do want to cover how it took over a bunch of the communities now. So I will not take a question anymore because I only have 10 minutes left because I need to leave relatively sharp on time, unfortunately. And then maybe we can have still a few minutes for questions at the end, if I can cover the rest now. So the first big takeover after translation was in language modeling. And this was in very shortly after another, actually, I think 3 major different ways, all of which are based on the original transformer. First one, probably most well-known one, is GPT. GPT-3 you probably know very well. This is essentially just the decoder part of the transformer. And the task is simply to model all of the language. So it's not translation. You don't have a source sentence that you want to translate. You want to learn the probability distribution over all of the text that exist. Maybe in one language, maybe in all languages, it depends on your data, right? So you only have the decoder and that's it. You learn probability distribution over all the text in the world. And so there is not the cross attention part of the decoder, right? This is exactly the decoder picture, but the encoder is missing and the cross attention into encoder is missing. Then there is an encoder-only language model, which the most famous example is BERT. This is only the encoder part. And the training task here is you take a sentence or a piece of text and you randomly mask some of the tokens. Like you replace them by a special token that means nothing. And the task at the output of the encoder, you would like these to predict what was originally there as token. You do this for, I think, 15% of the tokens in the text and you have BERT. Right, there is a second task in BERT, but I think of this one as the core one. So this is encoder only for language modeling. Then there was T5, which is the full encoder decoder, and it basically poses a lot of language tasks as translation. For example, okay, clearly you can translate English to German. This is good, would be an input in the source language in quotes. And then the output expected is das ist gut. You could do summarization, like as input, you give summarize and then blah, 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 a whole news article. And as output, you expect that it should generate and then just a short sentence summarizing it. Or another task, you can formulate it as translation. The input would be, is this toxic? And then some text, like you look beautiful today. And the output we want is, this is not toxic, for example, right? So all kinds of language tasks transformed into translations and thrown at original transformer. That is T5. That was also a very successful language modeling task in NLP. So we have all the variants used in NLP. In computer vision, lots of people try to see a pixel as a token, right? And then we want attention from all the pixels to all the pixels, and we can understand the image very well. However, going back to the question earlier, this is crazy. Typical resolutions used in computer vision are 224 by 224 pixels. That's about 50,000 sequence length, which just doesn't work. And so a lot of works have tried to get inspiration from what works in computer vision, convolutional models. So maybe do attention only in a small neighborhood and then slide this over the image or something like that. These papers work, but were not really a game changer, and in the end are really similar to ResNets or ConvNets, right? The key breakthrough there was actually to take the image and don't treat pixels as tokens, but decide to treat patches as tokens. Like, for example, cut the image into patches of 16 by 16 pixels. And then each patch just linear project it such that we have a vector, and now we have our sequence of tokens. And this sequence is not crazy long anymore, and each token has a little bit of meaning itself, right? And then send this just to the regular transformer encoder with position embedding added, like everything that we know. And then at the output, just take out one representation and use classification task. In Vision, it's common to use classification task as pre-training on labeled data sets. And here, the key part is transform the input into tokens, but such that it's not crazy long or crazy large amount of tokens. And each token is like a medium level thing, like not too low level, not too high level. And we cover the whole input. In this case, it was cutting it into patches. I'm going to skip this side note. Then speech, basically the same story. Take your input signal, and this is a standard transformation done in speech. This transforming to a Meyer spectrogram is another representation of this wavelength. And then cut this spectrogram into pieces. In this case, these are all slices, and then send these into a transformer. There are some encoder-only variants, there are encoder-decoder variants, and very recently there was this paper from OpenAI called Whisper, which is exactly that again. Previously, there was the conformer, which is almost exactly that. They just sprinkle in a few convolutions here and there in the architecture, but it's not really important. All right, so again, like take your input, cut it into patches that are just a nice size, like middle ground, and then treat them as tokens, send them through a transformer. Then reinforcement learning. I like this one especially because it's especially nice. So this is, I should say, offline reinforcement learning. So you have your large collection of traces, like think of someone playing through a game, like an Atari game or Mario or whatnot. And they basically cast this as a language model. You want to learn the language of all of these traces. So what is a trace? It's observation, which can be pixel. So we do vision transformer thing. We cut it into patches. Each patch becomes a token. Then, this is a key point, they add the return. The return is the sum of all rewards that will come in the future of this trace. So this is a proxy of basically how good is the player of this trace, right? High means it will still get a lot of reward in the future. We know the future because these are all traces we collected. Then the action that the person took when it saw this observation, and then the potential immediate reward that happened, like if it collected the coin right after his action or something like that, and then continue. Treat this as a language and do a language model on it, encoder, decoder, or maybe decoder only, or whatever. Then you train this language model. Then at test time, you get your observation, you pass it through the language model. You choose your return. Let's say very high number, 9,999. You give it to the transformer decoder. And then you ask it like probability distribution over the potential next actions. So you kind of tell it, you have seen this, now please act like a super mega pro. What action would the super mega pro have done taken here? And it gives you the distribution over these, and then you play that, all right? Of course, you cannot abuse this. You need to use a return value that actually appears for the good players in your data set and so on. But this is like a nice way of using information that you have at training time, not at test time, but you can use at test time to like select what behavior you would like, right? And this was called a decision transformer, and it took over offline RL. And then there is extra nice parts. I mentioned this unification of communities. It's not just in learning from each other, but it's even in mixing modalities. So there has been a recent flurry of papers mixing image and text, just transforming all of them into tokens, sending them through the same transformer, and that's it. There has been quite a few of them, even like with video, with audio, with everything. And I want to quickly mention one important note about transformer efficiency. There is this very nice paper from some colleagues, Efficient Transformers, a survey. There have been millions of alternatives to attention that try to tackle the fact that it becomes very expensive as the sequence lengths get very long. This paper kind of summarizes them and the different ways they try to attempt this and so on and so forth. So this is really nice to get an overview. And then in the next paper, they actually benchmark all of these and create the long range arena, benchmark specifically to measure how good is a model at long range or long sequences. And the results or subset of the results is actually this. X-axis is the speed, Y-axis is the score on this long range arena. And what I want you to take away from this is original transformer is slow, but is the best. Modulo Big Bird. And any variant that seems to be much faster pays the price by being slightly worse. There is no silver bullet. Original transformer still seems to be mostly the best thing if you don't care about speed, if you want to get the best performance. Right, and with this, I will end right on time, and I thank you for your attention. I think if there is like one very prominent question, I can still take it, but then I have to run to the next meeting.